In this lab, we're going to be looking at bidirectional forwarding detection. So let's have a look at the topology. This is the topology that we're going to be working with. It's very simple. We've got R1, VMX R1 connected to a switch, and VMX R2 also connected to a switch. And I have both of these routers currently open. And all I've done at the moment is the IP addressing, so they should be able to ping each other. And we're going to run BFD with OSPF. So let me just see if I can ping the other side. And I'm able to ping the directly connected interface, but I'm unable to ping the loopback. Or I should be unable to ping the loopback, as I haven't done any OSPF configuration as of yet. Yeah, there's no route. So what we're going to do, we're going to enable OSPF. We're going to have a look at the default time it will take for an OSPF to recognize that a link is down. And then we're going to configure BFD and then run the same experiment again and see the difference, the time difference between the two. And what I will be doing, I will just run edit protocols OSPF area 0. Now the two interfaces that I've got are, don't show interfaces first, let's match on iNet. And I can see I have GE000 on this side and also loopback 0. So set interfaces, interface GE000.0 and set interface loopback 0.0. And we're going to make it passive because we don't need to send any OSPF hellos or updates or LSAs out the loopback 00 interface. Let's commit that and do the same on R2. And show interface ters match iNet GE001 over here at back 0. Edit protocols OSPF area 0. Set interface GE001.0. Alright, let's see if we can ping the loopbacks first. Well, maybe OSPF has not come up yet. So run show OSPF enable. Let's try that ping again. And now it's pinging. Excellent. And what I will do, I will just open up the switch and I will shut down one of the interfaces on the switch. And let's see how long it takes to recognize that the neighbor is down. So I will shut down the interface facing R1. Interface G0/0. Let's just shut that down. Alright. Now if I run back over here, run show OSPF. And it's still showing as a full state. Still showing full. Hasn't even recognized that an interface is down. Let's have a look on R2. See if it's any better over there. Run show OSPF neighbor. No, still showing as full. And now it's gone down. So that was like 30 seconds before it recognized any issues. And on here, it's still showing us full. And now it's gone down. So we can see there's like a 30-second delay with OSPF to detect that the neighbor is down and possibly reconverge and go over another link. And sometimes that's just not good enough. So we could try to run BFD and make sure that it detects an alternative path, or it detects that a neighbor is down a lot quicker by saying no shut. And it still takes a while for this neighborship to come back up. Now you could probably do this with adjusting OSPF timers, but even if you adjust OSPF timers, I think that the lowest time you can get is like 1 second, and it's like 3 hellos or something that have to be missed. So you're not going to get anything less than 3 seconds, but by default it takes like 30 seconds. Okay, so it's recognized that the neighbor is up. Now, if we're going to do BFD configuration, we do it under the OSPF protocol. So let's just say up here, and the command is BFD. Maybe we do it under the set area 0 again. Sorry, edit area 0. Set BFD. I think we're going to do it under the set interface GE00.0. Is it BFD here now? Oh, BFD liveliness detection. And we're going to say our minimal interval is 400, which is like 400 milliseconds. And we're going to also say our multiplier. Let's commit that. Now, when we do a run show BFD session, we can see that the state is currently down, and that's because BFD is smart enough to know that it hasn't received anything from the other side. So it will only come up once we've done BFD configuration on both sides, and let's do that now. And you could also see that our transmit and our detect times are not quite right, and that's because we need to see it from both sides. So set interface GE001.0 on this side, and our BFD liveliness detection, we're going to have a minimal interval of 400, and we're going to have a multiplier of 4. Let's commit that. Run show BFD session. Now we can see that it has changed. So our transmit interval is now 400 milliseconds. If you times that by 4, you get a detect time of 1.6 seconds. And let's put that into action and see if that works. So if we say run show OSPF neighbor here, we can see that the neighbor is up. Let's bring this interface down on the switch. Shut. We've shut the interface on the switch, and we can see that the neighbor has already been detected as being down. Boom, just like that, we see that BFD is actually working. And is it the same on the other side? Yeah, so it detected it in like less than a second, I would say, but our detection time is 1.6 seconds. So we can see that BFD works very, very effectively, and it works with most of the protocols, OSPF, BGP, MPLS, LDP. So that's it for this lab. It worked a lot smoother than I thought. Let's move on to the next one. So this will be the VRRP lab, and let's have a look at the topology. This is our topology here. We have a user, a PC, which I'll call user. It's connected to a switch, and then we have 2 VMX routers, VMX R1 and VMX R2, going out to an internet router. And on the other side of the internet router, we have a route which is 50.50.50.50. I've done all the IP addressing already, and I have the 2 Juniper routers open. So let's have a look at those. This is R2 and this is R1. Let's just see if we have reachability to both to the PC, the client PC, and also to the IP address, the 50.50.50.50 IP address, which is advertised on the other side of the internet router. So let's ping the PC first. And we have reachability to the client PC from R1. We also should have reachability to our directly connected interface on the internet router. which we do. I actually put that IP address in wrong, but it worked. Let's just put it in correctly, even though we saw that it worked on the ping. That's correct. And let's see if we have access to the 50 route, which we don't. Okay, let's do those same tests on R2. That's the client PC. Our directly connected interface on the internet router, and then the 50 route. Which we don't. Okay, so the first thing that I'm going to do, I'm going to set up a static route. And now I've done the static routing on both the client PC and on the internet router, so I just need to set up static routes on these two Juniper routers. We set up static routes under the edit routing options, and let's say static. (108.12.0.6) over here. Sorry, I forgot to put the next hop statement. Our next hop. Let's commit that and see if we've got reachability now, which we do. Same on R1. Let's just do set routing options static route 0/0 with the next hop of 108.12.0.2. Excellent. So I think we're ready to do our VRRP configuration, and VRRP is done at the very end of your edit interfaces after the address. Edit interfaces, and we're going to do it on our LAN facing interface. .0 family inet address, which is 10.1.1.1/24, and then VRRP. We're going to have the VRRP group as one, and the VRRP group must be the same on both routers. Now the first thing I'm going to do is set the virtual address as 10.1.1.100. Then I'm going to set the priority. Now R1 will be the master, so I'll set that priority as 150. I'm also going to set the preempt, which I think this is, if you don't set it, then the backup will not take over. So if I set it on the master, if the master goes down and the backup takes over, you need the preempt command on the backup, so it takes over from the master, and you need the preempt command on the master, so when the master comes back, it takes back over as the master from the backup. I also want to set virtual address, priority, preempt, what else? Oh yeah, accept data. If you don't put accept data, then you won't be able to telnet, you won't be able to ping or SSH to the virtual IP address. And on the master, I will set some tracking so that we could track it when the interface goes down. So set track for the interface of GE000.0 priority cost. And what the priority cost does is how much it will decrement, how much will it take away from the initial priority. So we know that the priority at the moment is 150. So if I say the priority cost is 60, when it goes down, or if something happens, then it will take 60 away from 150. And as long as the backup is higher than 90, then the backup should take over. I think that's it for our commands on R1. Let's commit that. And let's go over to, let's just have a quick look, run show VRRP summary. And we can see that we are the master, currently active. Our local address is 10.1.1.1 and our virtual IP address is 10.1.1.100. And if we wanted to see a bit more information, we could say run show VRRP detail, I think. And we see a lot more of the information here. We can see which group we're in, group 1. Our current state is master. Our VRRP mode is active. We have a priority of 150. Preempt is enabled. Accept data is enabled. How many virtual IP addresses we have, and what is the IP address of the virtual interface. Lots more information. We can see that tracking is enabled. Lots of stuff here. Nice. Okay, and let's do that same command over on R2. Edit interfaces GE000.0. Edit family inet address, which is 10.1.1.2/24, and we have a VRRP group of 1. Set the virtual address as 10.1.1.100. Set accept data. Set the preempt, and we're going to set the priority as 110. The higher priority wins, so R1 should be the master because it has a priority of 150. If I had set a priority here of something like 151 or 160, then R2 would be the master. But that's all we need for now. Let's commit that. And what I'm going to do now, I'm just going to start up our user PC and trying to ping the interface. And let's do a long ping. So ping 50.50.50.50. Repeat 1 million. 1, 2, 3, 4, 5, 6, yeah. But we should be able to see the ping continuing. I'm going to minimize R2. And we're going to see how many pings we actually miss. So if I say up 3, and then I say set disable, before I do that, let's just stop this ping. And let's see which route it's taking. I'm expecting it to take the path through R1, 10.1.1.100, which is the virtual IP address. And then the next address should be 108.12.0.2, which means that it's followed the path through R1. So if I say trace 50.50.50.50, and we're just going to see which path is being taken. Right, so it did actually go to the physical IP address of 10.1.1.1, which verifies that it is going through R1. And our second IP address is 108.12.0.2. Excellent. So I'll resume the ping. And we'll see how many packets are dropped with VRRP. So we'll say set disable on the interface. And I'm going to commit that. And we're looking at these pings down here. Let me just move this up a bit. Commit, enter. So we can see one packet is dropped. Oh, only one packet was dropped. That's excellent. Okay, that's all we need to see for the VRRP lab. That is showing that high availability is in full effect. Let me just stop this ping and do a verification that it's going through R2. So we'll run that trace command again. Trace 50.50.50.50. And we see 10.1.1.2, which means it's going via R2. And 108.12.0.6. And as a further verification, we do a run show VRRP summary on R1. We see nothing because the interface is disabled. Let's just start up R2. And when we do a run show VRRP summary over here, we can now see that R2 is the master. The local address is 10.1.1.2 and the virtual IP is 10.1.1.1.100. And we're just going to, as a final test, we're going to bring back up the interface and see if R1 takes over as the master. We say delete, disable, commit that. Go back onto R2, run show VRRP summary. Now we see that R2 is actually the backup. Run show VRRP summary. And R1 is the master. Alright guys, thanks for watching and we'll see you in the next one.